Good. So we're going to look at a number of um, applications of uh, integration. Um, as I mentioned before, this is just an introductory course, and there's so many applications of integration. But we are only going to consider just the tip of the iceberg, just a few, right? We're not going to get into too much of differential equations and its application to so many other things. No. So we'll start with this simple one, application to area, right? And basically the idea here, and I don't know in high school when you were finding the area under a curve, did you do that thing where, um, one second, yeah, where you take this area here and you divide it up into little trapezium. You all ever did that? Trapezium.
Yes, sir. We look at it in physics.
Oh, okay, okay. And then the area, the little area here might be okay. Um, the width of the strips, let's call it delta x, right? And then you find the area and so on. Eventually, basically, you have this, right? The sum of y okay, let me use sigma x from um, let's go from x equal to 1 to whatever, right? And that sort of thing. Um, so when they realize that this really, right, instead of this here, it's really the sum of all these little strips here, right? Area under this curve. And well, when you watch this, as delta x tends to 0, this approximates to the summation or the integral of y dx from, okay, x equal a to x equal b, right? So the area on the curve is basically the integral of whatever y is, right? Y will be a whole long function. You integrate that function with respect to x from or between the interval of a to b, right? I don't know why this ink is blotting again. If on the other hand, and that's when the curve, you're finding the area between the curve and the x-axis. But if you're finding the area, maybe, okay, we have a curve like this. One second, my pen is misbehaving again. Maybe you have a curve like this, right? There we go, like this. So there's a curve y equal x squared. And you want to find this area here from 0 to maybe 2. Or let me go 4. Or 4, right? I want to find this area here. So what you're doing now, you have to notice this formula here. It's the integral of x with respect to y from a to b, right? So what you'll do, you'll take this and you'll make x the subject. So x equal to, what is it? Y to the half, right? And you put that in the thing here. So integral of y to the half with respect to y, of course, from 0 to 4 in this case, right? Yeah. So not always will you be called upon to find the area between the curve and the x-axis. At times you're called upon to find the area between the curve and the y-axis. Maybe they'll tell you in the first quadrant. I mean, it's this piece, right? So you're not going to find this area this over here. Yeah. So these are the two key formulas you need to know, right? Of course, you have an open book test, so you don't have to remember nothing. It's all there, right? Just how to use them. Let's look at some examples. So look here. You have to find area bounded by the curve y equal e to the x and the lines x equals 0 and x equal 2, right? So that's your graph there, a little sketch of it. And you have basically have to find the shaded region here. I know there's a little thing in here. This is just to illustrate that concept I was showing you earlier. So you take a little strip and the area of that strip will be y delta x, right? Roughly that, right? And the area in this whole area here is if you take a number of strips, notice a number of strips from x equals 0 to x equal 2. And the strips are, well, the width of the strips are very small. Notice delta x tends to 0. Now that the evaluation of this expression is really this here, right? By what we call a limit definition, right? So as delta x tends to 0, delta x here we can now refer to as dx. The integral of y with respect to x from 0 to 2. So you integrate y, which is e to the x. You get e to the x, no change there. And you're evaluating it from 0 to 2. So what you do is substitute 2 in the place of x, right? So you get that there, minus e to the 0. That's that. And I guess I think a step is missing here. You can evaluate this in your calculator, e to the second power minus 1, right? Well, okay, they didn't actually give you a number, they left it like that. Okay, you have a horrible decimal, right? You follow that? This step, you don't have to write this. This is the root, where they got it all from. So it is this that you have to really do from here. This is just to use the original idea. This is how the mathematicians, Newton and Leibniz and company, that's how they will go about it. But we have advanced to the point where you're just applying the integral right away. Clear?
Yes, sir.
Okay, let's take another one. So you have to find the area between this curve and the y-axis. Remember I spoke about that, right? You want to find the area between x equals 4 minus y squared and the y-axis. Same idea, right? So x is this whole thing here. So we put that in the place of x there, right? Oh, by the way, you have to do something before. You have to find where the curve cuts the y-axis, right? So you put x equals 0 and solve, and you will get 2 and minus 2, right? So you know that, okay, the interval through which you are going to integrate will be from -2 to +2, right? So you, in the formula, this is the, I guess, the formula here. So in the place of x, you put the whole expression 4 minus y squared. That's what they did here. We got the end of the interval, the ends, the extreme points, -2 to 2. So you integrate that, you get that, and then you substitute 2 and -2. Right? Substitute 2, you get that. Minus, and then you substitute -2 and there again, and you get that. And when you evaluate it, you get 10 and 2/3. Follow that? So in the first case, it was the graph and the x-axis. In this case, You have it between the graph and the y-axis. Notice in this case, they gave you x equal to something. It was easy. Sometimes they wouldn't do that. They actually tell you y equal to something in terms of x. You have to have the good sense to rearrange the function to make x the subject, right? So be very careful with that. Follow so far? Of course, there are.
Yes, sir. Tracking.
I like that new phrase, Drakes, tracking. Okay. Yeah. They have these peculiar situations where you can have a negative area, right? And you have to use, again, good sense, common sense, and know that, well, you can have an area that is negative. You have to interpret what a negative area means, really, right? So, like, if you're finding the area bounded by this curve, and if you were to go from 1 to 2 and then from -2 to 1, the area between this region here is going to be a negative number, right? If you add that negative number to this positive number, you may get 0. And you say, man, how I get an area that is 0? You got to know that, man, even though this area is negative, you have to take the positive of it, right? So the total area will be just this area times 2. Right? Just keep that in mind. It can happen. Y'all follow that? You just have to interpret this negative result. Don't let it throw you off and you add up and say, oh, get 0. Right? You know that the area, when you watch the diagram alone, you have to have a positive value. You have 2 big areas shaded there. How come you get 0? Yeah, look at an example here. We're finding the area here, and it's negative. But you are going to use 15. You're not going to use -15. Do not report an area that is -15. Right? Report an area that is positive. So the total area really is 30. Right? Because it's 15 here and 15 here. This is the previous example, really. They just actually do the calculation here. Right? Good. So it can get more complicated. I'm not going to go, much more complicated. So what do you have? The area between 2 curves now, not the area between the curve and one of the axes. No. Right? You have a situation where you want to find the area between the 2 curves. Well, that's not hard, right? I think when, let me just give you a similar example. In high school, when you were in high school, you used to get like, okay, I remember this story here. You have this here, and you have to find the area between here. And what did you do? Anybody can remember?
Sorry, from the area sector and then and subtract.
Find the area of the sector. What else?
The area of the triangle.
And you do what with them?
Subtract.
You subtract. Very good, yes. And that's basically what you're doing here. That's what this is saying. If you were to separate these two, if you put this integral sign around the fx, and then the integral sign around the gx, it's really the difference of 2 areas, right? So what you got to figure out is which is the greater curve, In this case, f being the one on top here, gx being the one at the bottom, right? So when you find the area between fx and the axis, right, that is the x-axis, you're finding this whole area here, right? This whole area here. But then when you find between gx and the x-axis, you find this purple area here. So if you want the area between these 2 curves, you just have to subtract, right? Everybody follow that?
Yes, sir.
Yeah, so the area in that, I don't know if you call that beige or pink or whatever color that is. You find the area between fx and the x-axis, and you minus the area between gx and the x-axis, right? Of course, it takes some figuring out as to which one of the functions, and so is the upper one, which one is the lower one, right? And if you're not certain, you have a lot of graphing program I introduce you to, right? But usually, you can figure it out by just knowing some basic functions that you were exposed. Let's look at an example. So look here, you have two curves. Y equal x squared, you know what that one looks like. And then the curve y equal 2x minus x squared, right? Good. So you want to find the area between there. Well, first of all, you have to find where they intersect as well, right? That's an extra bit of work. You have to find that, put them equal and solve, and you get 0, 0, 1, 1, right? So you know that we're okay. If I come down here, right? You find the area between this curve and the x-axis. Then you find the area between this curve and the x-axis, and you subtract, right? And that is what is happening here, right? The greater curve is 2x minus x squared, and the lesser curve is x squared, right? You remove the bracket, and you solve. I'll follow that.
Yes, sir.
They didn't tell you to find where the two curves intersect. You have to know that you have to find that. Right? In the previous slide here, one would think that the A and B might be given, right? They might give you A and B. But in this one, they didn't tell you nothing about A and B. You have to figure that out. You have to figure that out using your knowledge of algebra. Got that?
Yes, sir.
Good. Let's switch to another little application. And this has to do with finding volumes, right? Finding volumes. And basically, when it comes to finding volume, just like you did area, right? When you were dealing with area, you took a strip and you kind of divide the area into little strips, right? In the case of volume, you're going to take an area now, and you are going to kind of move it through an entire interval, right? This formula is a little complex for you, but let me go to a real example and see. So if you want to take this curve, right? That is give me y equal fx, right? So that's this here. Oh, what's that? Yeah, y equal fx, and you were to rotate it. You were to rotate it. Well, I think they don't use the word rotate. They use the word revolve. Huh? Revolve it. Yeah, they do use the word rotate. Yes, I use the word rotate here. Even though they're confusing with rotation and revolution. Yeah, you revolve it around the x-axis. It's going to create a solid something like this, right? Good. So what you're basically doing to find this volume, it's like you're taking a slice. You notice that? A thin slice. Now the area of that slice will be what? It will be, notice here, y squared pi, right? Remember the formula for a circle? Y'all remember that? Pi r squared. So if you watch that circle, it's as though the radius is y, right? So the area of the circle is going to be pi y squared, right? Now remember y and fx is the same thing, right? So it becomes this. Now the volume is really by taking that area and moving it through or adding up as, like if you take this solid and cut it up into, an infinite number of slices, like a slicing cheese or meat or something, right? Slice it up, right? Well, the sum of that area is really equivalent to this, right? In the previous slide, they use a complicated, that's this here, watch here, right? They use a complicated formula. But simply put, forget that formula, use this one, right? The volume is really this area moved through the interval A to B, right? And you can actually take this pi and put it in front of the integral sign. And when you finish all your calculation, multiply by pi, right? So memorize this formula. And remember that this formula though is when you rotate around the x-axis. When you rotate around the y-axis, instead of y here, you have to put x here. And you have to integrate with respect to y and not x, right? So let's see an example or two. Cool. So okay, this is a derivation basically of the volume of a sphere, right? The volume of a sphere. And maybe, I don't know if high school they told you this. I think you learned this in high school under measurement, no? V is equals to 4 over 3 pi r cubed, or 4 toward pi r cubed, right? Now, where did they get that from? Well, they got that from taking this sphere, and if you were to slice it up, into little circles, and you add up all those areas, you will get the volume. That's what that is saying, right? So here it is, the area, notice, is equals to pi y squared. That's of one slice, right? And don't forget that y will be equal to the root of r squared minus x squared. I wonder where they got that from. Anybody can see that?
Sir, it's from well, they kind of using Pythagoras theorem, because if you
Yeah.
look on the diagram, they can figure out how y changes as x changes.
Correct, yes, right? So they got that from Pythagoras theorem. Good. So now you have your expression for the area. Now, well, remember you have to slice from positive r to negative r. So that's your interval, and that's what they have here, right? That's what they have here. Good. So your volume then is the integral of the area with respect to x from negative r to r. Well, we got our area expression to be pi times r squared minus x squared. Notice how they take the pi, right? And put it in front. And notice they multiply by 2. You know why? Because the volume really is symmetrical. So no need to calculate from minus r. Sorry. No need to calculate minus r to r. Do from 0 to r and multiply by 2. And that's what they did here. So they didn't evaluate the integral from minus r to r. They evaluated from 0 to r, but double the value, right? So this pi came from this pi here, but the 2 came from splitting this interval minus r to 0 to r, right? I hope you're following that. And you do your integration, you substitute your r, you do your calculation, and you get 4 towards pi r cubed, right? And that's where that formula came from. See, calculus was being used all the time, but you only use the end result. Okay, let's take another example. So here you have a curve, and the curve is from 0 to 1. And you're taking this curve and you're, the area that the curve makes, that plane between the curve and the x-axis, they're rotating that right away around the x-axis. And it creates the solid that you're seeing there, right? I wish you all were exposed to a little bit of pottery and so in high school. Long ago, for those of you who are going to New Amsterdam Multilateral, they actually had a pottery lab. And they have all these revolving, I don't know what you call it. And you have clay, and you can actually make all these things, you mix the clay and put it on top of this thing, and you put on the switch, and the thing will rotate. And you can make pots and all kinds of shapes you can make now. Yeah, I'm sure, and it teaches everybody destroy that school. I don't know what is left here now. Just a shell. Yeah. Anyway, so you get this solid. So we want to find the volume that is generated when you do that rotation, right? Good. So again, you split up the, it's as though you slice up the thing, you slice it up, you find the area of one slice, and then you move it through from 0 to 1, right? You don't even have to worry, you just apply the formula. So it's pi y squared from 0 to 1, and you integrate with respect to x, right? Bring your pi outside, that's what's happening here. When you square root of x, you get x, which is easy. You integrate x, you get x squared over 2. Substitute 0 and 1, right? Substitute 1 in the expression, and you substitute 0 and subtract, and you get pi over 2. This one was easy. What are you saying?
So you realize it's most of them teachers answering and them other students.
Yeah. I know they're there in the class. Nobody ain't asking me, so show me this substitution, how will you get pi over 2? They ain't even asking that rudimentary question and all. And as I said, who was the guy? Thomas More? He moved the book Man for All Seasons. I think in the story, they wanted to get his opinion. Anybody know where the statement come from? Silence means consent. Anybody know where it came from?
No.
Yeah, it's that book, the book. And let me tell you something, a lot of the expressions, sometimes you can't use it with people because they don't know where it came from. They don't understand what you're talking about. But in the story, King Henry, or what his name, he wanted to get rid of his wife. And for techie sweet lady, And I think this guy, Thomas More, was some religious authority. And they wanted his opinion. What you got to say about this king putting aside his wife to deal with this other lady? And, religious people, they want to curry favor with the king. They want the king and you follow because, what that could mean for the church. And he kept quiet. He just didn't say anything. And people came up with the thing that if you're silent, well, it means you agree. Silent means consent. I must check out that story. There's a movie, of course. There's a movie named Man for All Seasons, I think. Watch it. And that's where that simple statement comes from. Right? But the generation of today, all they're doing is watching a vampire and so that's why they don't understand when you call people a sucker, what it means, or you're a blood sucker. They don't understand that, but they don't understand when I say, silence being consent. Then they don't know what I mean, and that's why some of them get in trouble with the girls. The girls didn't say nothing, so they continue and they end up in the lockup. Yeah. So look at this one, another example here. In this case, notice the rotation is about the what? The y-axis here, right? Right. So if you have a function that you're going to rotate about the x-axis, sorry, the y-axis, the formula is a little different now. Notice here, we are integrating with respect to y, right? So you have to have a function of y. In other words, you have to have x equal to something, right? In your function. That's how your function should be defined. X equal to something, as you see here. X equal gy, right? And your new, well, it's not a new formula, it's just a modified version, so that now you are integrating with respect to y, right? As an example, look at this one. So where am I? Yeah. So you have this function y equal x cubed. You rotate it around the y-axis, and a nice a solid is created, right? So you take that area that that shaded area there between the curve and the y-axis, and you rotate that. And what would happen is that you create a volume, right? Certain this here, right? Good. And they want to know, well, what's this volume? What's this volume? Well, it's really this area. And if you were to move it through from 0 right up to 8, right? Good. So you have y equal x cubed, but you don't want that. You want to have the function in terms of x. You have x equal to something. When you rearrange it, you actually would have x equal to the cube root of y. You stick that in the formula, square it, bring the pi out on the outside, and then you integrate this with respect to y. You have these ugly fractions inside. Substitute 8, evaluate it, then substitute 0, evaluate it, and then you subtract. And you will get this horrible looking value. Right? And that's your volume. Sometimes the volume is rotated about the x-axis, sometimes it's rotated about the y-axis. Any questions about this one? All right, good. And of course, as I told you, things can get more complicated and so, right? Like you have a situation where, just like you had two curves, and you have to find the area between the two curves, sometimes you have a volume where the whole thing is solid. Like how you have, look out here. Like you have a hollow inside there, right? The middle is empty. So it's really, you're taking two curves, the area between these two curves, and you want to rotate it about the x-axis. Now the volume that will be generated is given by, notice, the difference, right? You find the difference of the two curves, and the two curves are what? Let me see, x squared and what's the next one? Oh, the line y equal x, right? So you have two curves, y equal x, and you have y equal x squared, right? Notice in this case, y equal x is the greater curve, and y equal x squared is the lesser one, right? I know it looks funny, but yeah, the diagram will show it. Good. Now, if you were to take that intersection and rotate it about the x-axis, you'll have this shape, right? You'll have this shape. Right? Good. So the volume that is generated, right, is given by this formula. This formula here. Right? Notice the you have to square x, so you get x squared, and you have to square x squared, so you get x to the 4, right? Pi there, you can always bring that to the front. And the intersection, this 0 and this 1, you have to get it from solving where these two intersect. You have to solve those two. Now, in this case, notice you're not given that. You have to figure out that, these two curves intersect at 0 and 1. And there's where you got those interval values from. You do your integration, you substitute your 1 and your 0. When you finish all that, you multiply by pi, and you get your answer. Right? And that's how, when you have not just a single function, but you have two functions, and you're finding, well, okay, the solid that is generated, then you take the area between these two chords, and then you rotate it, whether be it along the x-axis or the y-axis. Yeah, well, this is another way of doing it, right? Finding one volume, then finding another volume, and you subtract. Same thing you'll get. Right? So something will get more complicated. That's what this is explaining. So we end here. I don't want to get into too many more of these.